All right, let's get into it. We are right on the edge of this massive, massive shift in how we power our planet. We're moving from energy on land to grabbing all that incredible power waiting for us out in the open ocean. And to do it, we're building something that sounds like science fiction. Electric superhighways under the sea.
Seriously, just picture it. We're not talking about your typical power plant anymore. We're building these gigantic offshore wind farms that are becoming some of the largest renewable energy zones anywhere on Earth. And these aren't just a handful of turbines, you know? They're like sprawling cities dedicated to clean energy, miles and miles from the coast.
And this isn't just some idea for the future. It's happening as we speak. I mean, look at this project in India. It's this enormous effort to connect one of the world's biggest new renewable energy parks straight to the national grid. The scale here is just mind-boggling.
Just how big are we talking?
2.5 gigawatts. That's the capacity for this one single corridor. Now, to give you some perspective, that's enough juice to power millions of homes. It's a colossal amount of energy, and it's all being made way out there, far from where we actually need it, and, well, that creates a pretty big problem. So, okay, you've got all this beautiful, clean power. Great, now you got to get it to shore. And when you're dealing with hundreds of kilometers of ocean, the way we've always done things, well, it just doesn't work anymore.
Right, this is the big question, the one that engineers had to crack. I mean, pushing gigawatts of power across huge distances, all underwater, that is a massive technical challenge. So what's wrong with just, plugging in a regular old power cable?
Well, the old school method uses something called alternating current, or AC. The problem is, when you send AC power through a super long undersea cable, it starts to lose energy. It's kind of like trying to send water through a really, really long leaky hose. By the time it gets to the other end, you've lost a ton of it. It gets super inefficient, and pretty quickly it just stops making any financial sense. So if the old, leaky, country roads of AC power aren't going to get the job done, we need something better. We need a whole new kind of infrastructure. What we need is an electric superhighway.
And that superhighway has a name, High Voltage Direct Current, or HVDC. This technology is the absolute key. See, by using direct current, we can pump huge amounts of power through those undersea cables with almost no losses. It's the big breakthrough that really makes these giant offshore projects possible.
So here's the basic idea. Over on the left, you've got the wind farm making all that power. It gets sent through that long DC cable in the middle and then connects to our grid on the right. It looks pretty simple, right? A nice point-to-point connection. But the real magic, the secret sauce, is happening inside those two boxes, the converter stations. This right here is the heart of the whole system. This is the converter station. It's basically a giant, high-tech box where all the heavy lifting happens. It's just packed with these super advanced electronics that manage every bit of that energy flow. So what exactly is its job?
You can think of the converters as the on-ramps and off-ramps for our electric superhighway. You see, the wind turbines make AC power, but that's not what we want for our super-efficient, long-distance DC cable. So the converter station offshore acts as the on-ramp, changing the power from AC to DC. Then, once all that power gets to land, the other converter acts as the off-ramp, switching it back to AC so it can flow into our homes and businesses. Simple as that.
Now, as you can imagine, building a system this powerful and complex has its own set of challenges. It has to be incredibly tough. It can't just work on a sunny day. It has to handle major, unexpected problems on the grid it's feeding into.
So let's play this out. The wind farm is just cranking, pumping out gigawatts of power, sending it down the superhighway. But then, bam! There's a problem on the grid on shore, a short circuit. The off-ramp is suddenly blocked. What happens to all that power that's still flooding in?
Well, you get a massive electrical traffic jam. All that power has nowhere to go, so it just piles up in the system, and this happens unbelievably fast. We're talking 30 to 50 milliseconds. That's faster than the blink of an eye. This huge power pileup creates a dangerous voltage spike that could fry the entire system. So, how do you stop that from happening?
It turns out engineers came up with this really clever two-stage solution. First, the moment that fault happens, the system's own capacitors act like a big sponge, instantly soaking up that first wave of extra energy. Then, if there's still too much power in the line, this other piece of gear called an energy dissipation device kicks in and safely bleeds off the rest of the excess energy as harmless heat.
And it works beautifully. This here is a simulation of a really bad grid fault. Take a look at that top line. That's the voltage on our superhighway. You see that little bump right when the fault hits? The system immediately catches it and brings it back down, keeping everything well within safe limits. The system basically just shrugs off the problem without even breaking a sweat.
All right, let's talk about the money, because this technology is amazing, but it's also a massive, massive investment. So why do we choose HVDC? Well, it all comes down to a really important economic trade-off. You can basically break down the total cost of one of these projects into two big piles. First, you've got your terminal costs. Those are the big, expensive converter stations at each end of the line. Then you have your route costs. That's stuff like the actual undersea cable and, importantly, the cost of all the energy you lose along the way. And here's the trade-off. HVDC has way higher terminal costs because those converter stations are really complex and expensive pieces of kit. But its route costs are much, much lower because the DC cables are way more efficient. Traditional AC is the exact opposite. The stations are cheap, but the route itself is really expensive and leaky.
And this graph, this is the billion-dollar crossover point. It shows cost versus distance. That blue line, the old HVAC technology, starts out cheaper, but the farther you go, the more expensive it gets, and fast. Now look at the purple line, HVDC. It starts out more expensive, but its cost goes up much more slowly. For any big project that's far from shore, there's a point where that purple line crosses below the blue one. And from that point on, HVDC isn't just better technology, it's the cheaper option.
So you can see this technology is about way more than just hooking up one wind farm to one spot on the coast. It's actually laying the foundation for a totally new, interconnected energy future.
That's because HVDC isn't stuck just doing simple point A to point B connections. We can actually build complex networks with multiple on-ramps and off-ramps, real supergrids under the ocean. Think of it like our national highway system connecting all these different cities. These supergrids can connect lots of different energy sources to lots of different places.
Just imagine a grid that links up the offshore wind farms of, say, several different countries. If the wind isn't blowing in one spot, another area can pick up the slack and share its power. This creates a much more stable and resilient power supply for everybody, and it lets us share clean energy across borders, making sure the lights always stay on.
At the end of the day, the technology to build these incredible energy networks, it's not a dream. It's here, right now. And that kind of forces us to ask a much bigger question. If we now have the ability to build electric superhighways across entire oceans, what's really stopping us from creating a truly connected global power grid that runs completely on renewable energy?